So hello everyone, welcome to the lecture number 10, I believe 10, yeah, where we will just pick up where we left off last week, because we are almost at the pivotal point. So we ended at listing some properties of norms, operator norms, because we are preparing to show that the evolution operator, which is defined by a series, that this series converges absolutely uniformly, and the radius of convergence is infinite and stuff like that. To make sure that our that evolution operator is very well defined indeed. So we have our operator norm, which is necessary. It was necessary because the procedure for showing convergence of operator value series, especially operator valued function series, was to, you bind it with something, some positive value, number value series, and you go from there, right? So we needed norm to construct the bound, essentially, and then go from there. So so we have a norm, we have properties, so now we can actually do it. So let's start with writing down bounding series WK for evolution operator. So our evolution operator, the terms of it, that would be, so a norm of minus IT, t is time, to power k, k factorial, h to power k. H is Hamiltonian of the system. Just to, if you forgot somehow, right, that our evolution operator supposedly is this. Oh. Tk. Right, the Taylor series for exponential functions, right? Just to remind us. So now we have to, so this is a norm. We already know that the series made out of norms is a good bounding series. But here we can use a couple of properties of the norm to maybe simplify it a bit. So one, these are scalars. So we have this scalar scaling of operator norm. We can just pull them out. So the absolute value of time to the power k, we can just pull it out. And now there is a Hamiltonian. So we have a power k of the Hamiltonian norm of this. So this just asks to use the sub-multiplicativity of the norm to convert this guy into tk norm of h to power k. However, yesterday I learned that for normal operators, it's actually equality. Normal operators, normal ops. So operator is normal when it commutes with its own Hermitian conjugate. Okay, or you can equivalently you can write like, maybe this is the form you saw somewhere. Oh, not h. Right, this equality holds. So these are normal operators. Hermitian operators obviously are normal because it's a Hermitian operator is equal. It's a conjugate. Unitary operators are also normal, right? This is a whole class of normal operators. And for those guys, actually, For normal guys,
so not for us.
it's equality here. Yeah, so not for us. For normal guys, so not for us. Which is like, oh, that's so cute. So we don't, we can actually write here equality, which is basically very nice. Okay, so one more thing. So what I like to do here is like actually revert back the pulling out of the scalar, because I want to have unitless parameter here, t times h, the norm of it. Okay, because t times h is t has units of time, of course, h has units of frequency, so multiply them have unitless quantity. So we have our bounding series. We can call it wk, okay. And I mean, we started from the Taylor expansion of the exponent function here, right? So this is basically, this is a series that defines exponent for a value t, norm of th, right? So we immediately know from 0 to infinity wk. If you look at this, so this is k equals 0 to infinity th power k over factorial. So this is nothing else but exp normal number exp. It's just a function. So we know that this bounding series converges, and we even know the value to which it converges. It's an exponent of this norm, which is finite. Okay, so it converges. So we know that our guy converges. I mean, our evolution operator, because it's bounded by convergent series, it also converges absolutely and uniformly within the radius of convergence of the this bounding series. What is the radius of convergence of exp, of function exp? Well, we can check, although you probably know. So radius of convergence, if you remember, was 1 over the, yeah?
Regarding the previous inequality, first of all, it depends on time. The previous one, the last one. So first it depends on time. And also, does something happen at t equal to 0? Like
something happens with equal to 0.
UK is bounded by 0. That's not a problem.
Yeah, but value, no, it's not a problem.
Yeah, okay. And because this is the bounding curve, so the other things will come below it. So if this becomes 0,
it's not. I mean, exp of 0 is 1.
Okay.
So the norm of norm of identity is 1.
Mm-hmm.
Then, I guess, which is sensible. Norm of identity should be 1 because it does nothing to the vector.
Mm-hmm.
No stretching.
Identity square wouldn't be identity, which would be weird.
It would be weird, yeah. But the radius of convergence, because we want to see if this actually depends on t or not. So if you remember, the radius of convergence was this ratio test, but inverted, 1 over ratio test. So it was limit k goes to infinity, and we ratio test for the power series, which exp is the power series, right? If we treat this norm here as an argument, then it's the coefficient is 1 over k factorial. So we take k plus 1 factorial, that would be k plus 1 coefficient, right? Divided by 1 over k factorial. And we get 1 over this to get a radius. So this is ratio for ratio test. 1 over it is will be the radius of convergence for our power series. And this, of course, is quite not difficult to compute. K to infinity. So what we will get here, 1 over k plus 1. Okay? Which is, it's easy to calculate the limit, is 0. 1 over 0 is infinity. Okay? So so in other words, exp has infinite radius of convergence, which means that it converges absolutely and uniformly in the whole space, everywhere, for whole complex plane. So because disk 0 around R going to infinity, that equals the whole complex space. Therefore, so the bounding series converges uniformly. Converges. It has radius of convergence of infinity. Therefore, our evolution operator converges uniformly, absolutely everywhere. There is no constraint on it. The best thing you can have. Okay? And because of this is justification why in the very beginning we could differentiate it term by term. Because if you remember from previous lecture, the uniform convergence was required to be able to differentiate term by term. And we could also, so this was the justification for why it satisfies Schrödinger equation and stuff like that. So this is the reason why we could do it. It was legal. Next thing was we could the composition rule for unitary evolution operators. So we could multiply one evolution operator times other evolution operator and do it term by term, sum everything up, and we get our result. This was legal also because of this absolute convergence in the whole space. Okay, so this is the justification. Previously, we did it under the threat that maybe something explodes, but nicely, exponential function is the blessed, is the divine function. Everything is good for it. Okay, so also making an operator function of, the exp of operator is also good because exp itself is very good. So this is like an ideal. There is nothing more you can want, okay, from functions and from series. Maybe the inverse of exp, logarithm, is not blessed, okay?
It's cursed.
It's cursed, okay? It has complications. So maybe the ideal, the real divine, the God of gods of all the functions would be something that converges everywhere uniformly, absolutely, and also its inverse is such. I guess identity function.
Yeah, because it's a function that has to be its own inverse.
Constant function is such a, so nothingness. So the God of gods is chaos, is nothingness. Okay.
Well, chaos
okay, not chaos, nothingness. The void. Void is the God of gods. Then, and beneath, its archangel is its Valar is a exp. That's our mythology and theology of quantum mechanics or mathematics. I have no idea what I'm talking about.
Myth of creation of Hilbert space.
Yeah, I have no clue what I'm talking about. But let's move on to something completely different.
Just a prophecy.
Yeah, it was just So that was an example. So evolution operator we just checked is an example of everything is fine, everything goes smoothly. So I thought that maybe it will be cool to see an example where things are not as smooth. because not all functions of operators are just, have no problems. There are some that where things get complicated, and even so, those functions are still supremely useful. Okay, maybe not at this very moment, but eventually, and almost surely next semester, they will come up all over the place. So let's check the example of less divine function would be something that's called resolvent of Hamiltonian. So there is this thing called resolvent of H, which is the symbol. This is a symbol, okay? And it's defined by a series, von Neumann series, if you want to check it out for yourself. Hk divided by zk plus 1, where z is some complex number. So it is a function of Hamiltonian, yes, but also of this number z. It's a matter of interpretation of which is an argument of this function. But this is resolvent, okay? And this is a series that defines it. So the thing to check is, okay, well, what about convergence of this guy? Because it's like you might see that what if just by looking at this formula here, you are immediately, what if z is one of the eigenvalues of H? Then it's kind of like, whoa, blowing up. I mean, this is why it's written like this, to show that there are some points where things are blowing up. So there will be some. If it converges, then the radius of convergence or the domain where it converges would be something non-trivial. Okay, it won't be whole space for sure. Okay, there will be some conditions. So let's check out those conditions.
So I remember from like this complex series you had this. So first of all, you can think of this like a geometric series, and now depending on how you write 1 minus h over z or z by h minus 1 will have different radius of convergence. Right? So it seems that you chose one.
It's all connected. Yeah. Okay. So we will check this out immediately, and we see the connections with geometric series actually. So if we want to check convergence, of course, we have to find the bound for our series. So in case of this resolvent, so we have the norm of our series. I can write it like this. Hk, right? So that will be a norm of a term from our series. I write it like this. So again, what I would do here then, if I didn't knew about normal operators, I would bind it from above with z absolute value k plus 1 and h to power k. But actually, we now know if h is a Hermitian operator, we can just write equality here. So the series of norms is already a good binding series. I mean, it's a power. Okay, so whether this is a term of a power series, it's kind of a matter of interpretation, because if you look at it as if this norm of H is an argument, then it's a straight up power series. But maybe it's actually 1 over z is its argument. Then it's not really a power series. Or maybe this is a geometric series with some fixed common ratio. Something like h over z. A matter of interpretation, how do you choose to view this bounding series. But whatever the case, we want to perform a ratio test for it to see if it converges, where it converges, how it converges. So let's write ratio R. K goes to infinity. Z minus K plus 2. H K plus 1. In the numerator and denominator, minus K plus 1. H K. Again, fortunately, very simple to calculate because everything cancels out basically, and we get H over norm of H over Z. So actually, limit is unnecessary here.
No.
Right? So this is like an argument for it being actually a geometric series, right? Because this is the ratio test for geometric series would give you just a common ratio. So now if you want it to converge, this would have to be smaller than 1, right? This is the ratio test speaking. But if this condition is not always satisfied. If you are given the Hamiltonian, it has some norm. Z is like a parameter here, so not for all Z's this will be satisfied. As a matter of fact, we get, so for this to converge, the absolute value of Z has to be greater than the norm of H, which also, it's nice to remember that this is connected to the spectrum of H. If you remember from previous, so this symbol is like the maximal absolute value of the eigenvalues of operator H, right? So this is like, so Z has to, which makes sense, you know.
Must be out of the circle
Yeah,
of the spectrum.
exactly. So there is no threat that it will actually, Z will intersect with one of the eigenvalues and this will blow. So this notation is kind of insinuates a lot, and it's confirmed, you know, that it's a good choice of notation. I mean, there are other reasons why it's a good choice of notation. So this is like Z has to be bigger than something, okay? And also we can bind this guy. This binding series can be bound itself. Because this binding series, okay, if you think of it as a function of Z actually, okay, then it's like, so let's bind this function with something to see if it's uniformly convergent, okay? So if you think about Z that are, you know, we are, if we think of Z that satisfy this, okay, then we can pick some arbitrary epsilon greater than 0, and we can set Z, if we choose, what am I saying here? Okay, so we have access to Z's that are greater than norm of H, so that so the ratio test is satisfied. But this guy will be this guy can be bounded from above by H, K, and we can put into denominator H. So we're like on the verge, on the border, where the ratio test is no longer applicable. So we want to slip a little bit, add some epsilon. Okay, so we moved from the border to the safe space.
But epsilon is positive.
Epsilon is positive. It's arbitrary small epsilons. Okay, and this will be bigger, right? Because we are those z's, they have to be bigger than. I mean, we can always, for z's that satisfy this condition, we can always find an epsilon that will do something like this. And this guy, this series, it's actually convergent. 1 to infinity. H plus epsilon k plus 1. Because I can make out of it a geometric series. So let me pull out the excess power of the denominator, so that I have a sum over k going from 0 to infinity of modulus h, norm of h divided by norm plus epsilon, so something that's smaller than 1 to power k. And I also have to add and subtract 1, because I'm starting my sum from k equal 1. And this is a geometric series for a common ratio that's smaller than 1, evidently. So I can sum it up. There's a formula for it. And the result is 1 over epsilon minus 1 over norm of h plus epsilon, which is not infinity, okay? So this guy converges, and it bounds our bounding series, which depends on z. Therefore, we found it's uniform, where it converges uniformly, absolutely and uniformly, and therefore resolvent also converges uniformly, absolutely. However, not inside a disk of some radius, but actually in the complement of disk. Because our condition is you have to be bigger than something. So it's like, is it a radius of convergence? It's actually the domain of resolvent. Resolvent, that would be z's. If you treat it as a function of z, which is a complex plane minus the disk. It centers at 0 and of the radius equal to the norm of the Hamiltonian. So this silly calculations, I wanted to show you that it's not always so easy to figure out where your functions of operators or your series converge. Sometimes it's straightforward, some power series here and there, and you can, okay, there's this radius of convergence, everything inside is nice and good. But sometimes you have important examples where you get something that requires a little bit of gymnastics to figure out where it converges, when it diverges. Not a clear-cut picture, and you may get something surprising. That it's no longer a radius of convergence, I guess, because it's not in disk, but outside of the disk. How to call this? I don't even know. This is the domain of, I guess, of convergence or whatever. But it's still uniform and absolute and so on and so forth. So there are even more powerful statements you can make that it's a resolvent is actually an analytic function. But all this stuff will come back at some point when we get in the next semester to talk about green functions. This will be like we will breathe this stuff. Okay, all those things will be very important for us. A question.
So that inequality can go back. So here this is like, is it because of the uniqueness of series, this geometric series can equally be thought of as a Lorentz series, right?
Is it Lorentz series?
Yeah.
Lorentz
Yeah.
series.
It should be the same.
Yeah. Because these are all this stuff is very connected to functional analysis in complex complex functions.
We have this Pano reset behavior with like setting denominator series, but it also depends on how you want to interpret it. Yes, because if you're thinking of HK as the parameter, then you're...
Of course, the complication here is that we are intermixing with operators inside, right? Not numbers. So, however, I mean, I imagine that this is my plan. The next semester, I have this itch I have to scratch. I maybe will try to talk more about actually functional analysis, so the contour integrals, Cauchy theorems.
Complex analysis.
Yeah, because this there is whole branch of mathematics and very useful tools to deal with operators, Hermitian operators especially, but also much more, that basically transports the problem of operators into the complex functions, and then everything, you do your contour integrals and stuff like your series expansions, Lorentz series expansion, all that stuff, and then spectrum of the operator becomes like the thing that controls everything, and you can talk about bounded operators, unbounded operators. It's fascinating stuff, very useful. We will actually use it for some Schrieffer-Wolff considerations as well. So, but no details right now. I don't want to go into a lot of details right now. I want to save it for the next semester, so that I have time to learn it all before I start talking about it with some confidence. But Resolvent is a useful thing, and you shouldn't be afraid of it. So we can be friends with it, and I have a assignment for you actually, because this also this formula, it also like suggests that it's like 1 over, so it's like inverse of z minus h maybe. So the assignment is to actually prove that Resolvent is actually an inverse of this kind of operator. Of course, within its domain where it converges. So you just have to do the calculation and check that indeed it is 1 over. So not only the poles where stuff explodes.
But how do we do it? We just expound one the other term by term?
Yeah, I mean...
Okay, we just expound the one, the other we do not expound, there's nothing to expound, yeah?
Yeah. So you are working in this domain where it converges uniformly, absolutely, so you can just expand in the series and do whatever you want with it. Because it will converge eventually. That's why we checked, and
Oh,
right?
But by the way, because as far as I understood, this is this thing that when you have a series, you shouldn't shuffle terms or something like this because it can change the... Yes.
That's conditionally convergent series,
Yeah, exactly.
The abominations.
Yes, but on the other hand, in principle, even if I have a conditionally convergent stuff, can I just simply take terms out of the bracket? Like, let's say, I will just take t in front of the whole series so that every term is divided by t. Is it like causing some hazard?
Yes.
This one as well, okay.
Yes. You would have to check at every manipulation requires then verification if you are breaking something.
So I thought like multiplicative modifications are not a problem.
I mean, if switching the order at which you are summing, cause you can obtain whatever value, you can imagine that it's so everything can happen. That's why we are dealing with absolutely uniformly where none of this can affect anything. This is the most robust, most resilient.
I think we are simply lucky to deal with them. It's also that we chose it. For us.
Maybe it is luck, or rather this is like.
In cases, it is like that.
Yeah, if it wasn't like that, then nothing would work. You know, this is like the survival of the fittest, basically. It's like everything else would just. These are the structures that can support anything.
So all the universes with other evolution operators simply already collapsed, and we are living in the best possible universe.
Yeah, I mean,
collapsed because
they never existed, maybe.
Yeah, that would make sense. I mean, that's.
They didn't start it.
Maybe fun to think about it, but I don't know how. I don't know how to start. If we had some examples of failed universes, then maybe. But yeah, it was like, you know, we don't have to worry about this stuff. And so that was fun, at least for me. I don't know if it was fun for you. But now we can move to actual things, actual perturbation theories, eventually. Because we know, now we have our evolution operator. We know it works. Okay, so let's calculate it a bit using some perturbative means. Because, you know, it's an infinite series. I mean, series with infinite number of terms. It's a limit. It's not it's not a number. You have to calculate it first to have a value, right? You have to do something about it. So I will introduce then something I called here. I don't think there is a canonical name for what I'm doing right now, but I will call it the basic perturbation theory. Implicitly for evolution operator, of course, because what else we have here? We call it basic so that I can, when I refer to it, you will know what I mean. So the thing I will describe here will be the basic perturbation theory. So the idea is that, we spend a lot of time talking about convergence, what it means, that it's a procedure, that you make this contract that when you do a manipulation at the end, you can approximate this symbol with any accuracy with some value, right? So in a sense, the very idea of convergence series already gives us some prescription for doing approximate calculations, right? So like the basic perturbation theory would be basically let's just fulfill this contract. Let's just calculate some partial sums to some accuracy. So that's some kind of perturbation theory, I guess. We will talk about if it's really a perturbation theory, but it's a thing we can do, and this is what I would call a basic perturbation theory. So this gives us a prescription for nth order approximation to UHT. Okay, would be simply a partial sum of some number of terms. So I use this notation capital E, capital letter with n, which is sum k go from 0 to n. And our terms here. So that would be IT k divided by k factorial h k. So that's the most basic thing we can do. We are basically fulfilling the contract of the series.
Taking just n parts.
Yeah, n terms. So, couple of things. For one, because this is a series that converges absolutely, we already know, by looking at the Cauchy criteria for convergence, that this means that how did I word it here? Yeah. I had this nice sentence here. Okay, whatever. But the idea now that it converges absolutely, therefore, there is like a finite number of terms you have to take to get a value that's, you know, epsilon close to the exact value. And you know also that if you take more terms, you will just increase accuracy. It will never go wrong. So it's like basically we know that just by adding more terms, we will improve accuracy. And if we can go far, we can make this arbitrarily accurate, basically. If we are patient enough, if we have enough resources, we can achieve any accuracy we want by just adding more terms. Okay, and then nothing can go wrong. It's not like the term at some point at order of 1 billion, the thing starts to, you know, explode and behave erratically. No. Everything is nice. Nothing extraordinary would happen. We just know adding more will improve accuracy. And there is some finite number that gives us certain accuracy that we pick. So for every accuracy goal, there would be this number of terms we have to add to reach it. And it might be a question. So okay, so how much? Let's say if we set accuracy goal, how much terms we need to take, how much work we have to put in, which will be basically identifying this threshold index n of epsilon. Or the other way of looking at it, maybe more practical, if we put some amount of work, so we calculate n order, what is the error we are making? So it's like either we want to target some accuracy goal, then we have to know how much we have to add, or we add something because this is what we are patient to do. What is the error that we incur in doing this way? So let's start by first checking the second option, that is what kind of error we incur by doing n-order approximation, because this would be easier to find than the other thing. What is the optimal number of terms to give you a given accuracy? So to check what is the error, the most straightforward thing to do is to basically, you're doing, maybe there are some trickier way to do it, but you basically try to estimate what is the difference between exact, so infinite number of terms, minus our approximation, take some, measure it with some norm, and maybe compare it to, how it compares to the exact value. And try to estimate it, because of course, yeah?
So here, I don't see where the perturbation is coming, because now we are just approximating an evolution operator. So why did
yeah. You come in and spoil all the, I'm preparing narrative here, it's like, and he comes in, he understands everything, it's like, oh, but is it really a perturbation? It is perturbation. For now, we are in the blissful ignorance. We still believe this is a. Come in and spoils all the fun. Okay. Have some tact, It's like. Snape.
For a moment.
But Snape killed the Dumbledore. It's like.
I asked whether if I missed some of your arguments. That's
no, I was omitting. I am omitting.
Oh, you found it.
Yeah, you already, you saw through me. You read me like a book, basically. Okay, so let's estimate the reminder. Reminder, okay? So how much error we incur by doing an order approximation? So the thing is, so we take a exact evolution operator, subtract from it the n-order approximation, measure it, so norm, and maybe just for fun, because it actually makes sense, compare it with something. So let's say with the exact result. So you express your error in percentages, okay, something like this. And of course, this is not something you can calculate easily, because you would have to know this first of all. But we are trying to approximate it. So you have to estimate it somehow. So here comes the what can you do? And in this case, there is because exponent is a blessed function, blah blah blah. Series is blessed. There are tricks you can do to actually go quite far. So let me keep the denominator here for the second, and let's focus on the numerator. So on one hand, we have our series goes from 0 to infinity, not k, t power k over k factorial h, right? And we subtract from it a partial sum. Goes from 0, but only to n. K factorial h. Okay, so this is, so we can subtract it. Everything converges nicely, so there is no penalty for doing some manipulations on the series and the partial sums. So we get norm of starting from n plus 1 to infinity minus itk. K factorial h k. Okay, that's something at least. But now, the thing we can observe here, this is one of the features of exponent, that it has this kind of fractal structure. So if I take the first term of this series, it will be t to power n plus 1 divided by n plus 1 factorial h to power n plus 1, and let's just pull it out from under the symbol of sum, because all the following terms will be of higher power of k, higher factorial and stuff like that. So we can pull out yes, okay. Sorry, I had for a second there, I was like doubting myself for a moment. N plus 1 plus k from 1 to infinity Okay, this is a nice feature of, I mean, this is why it's this equation, Schrödinger equation looks like it looks. Okay, that's basically, this is the reason that you can do stuff like this. And this guy here, this is just u, ht, okay? And therefore, I can do now sub-multi.
How did you go from upper line to second line?
Is there something wrong here?
No, I couldn't follow. Like from k equal to n plus 1 to infinity.
Okay.
Then you wrote down minus it to the power of n plus 1. Like from there to the second line.
Yeah, so that's this is the first term, right?
And the second sum should be k equal to n plus 2.
2, yes.
That under brace part.
You ignored n.
In the second last line, the under brace part, that summation k equal to n plus 2 to infinite. That's the number.
N plus 2.
Because now you are starting from the very beginning.
No, but I pulled it out. The powers, I put them out.
Even then, you
put just
one factor, right?
No, but
it will be like 1 x square x cube, and
okay,
take x cubed 1x from x. That doesn't make the summation change, right?
So we have this guy, right? T.
Because you are adding one constant power, you are not removing one power.
Right. The next guy is minus I th and plus 1 minus I t h and plus 2. Oh,
You wrote the same thing.
oh shit. N plus 2.
Yeah.
That 1 second you doubted was correct.
Okay, so I doubted myself and now that was correct. Wait. No. I'm
So we just, so what are you taking common from all the terms?
wait, I'm like
1
Yeah, by
to power 2.
square
plus 1
n plus 1
factorial
And
times
plus
n
3.
plus 2 times n plus 3. Right?
Let's just wait
Yeah.
some minutes.
n plus 3.
No, because n plus 2.
Plus 2.
You don't need n plus 2? Or because that,
N plus
yeah,
2.
exactly, yeah.
This is true. Wait. Okay.
Sorry to ask question.
No, it's like you're following the steps, so that's good.
Wait.
Wait.
So it's everything
Wait.
about this
Okay.
quantum mechanics.
I don't think so.
I go home.
You broke quantum mechanics.
Everything doesn't make sense. We can just leave.
Maybe Einstein was right.
Oh gee. Oh gee. Wait.
But again, so you wanted to pull out that factor, right? So because we have to fix what we want to do.
Yeah, because I was like,
So then it's a matter of just changing the summation. Summation from k equal to n plus 2 or something. Yeah, n plus 2, I guess.
this denominator that it's like.
Yeah, this is the problem. Because it's not a power.
Yeah, it's not factorial anymore if you pull it out.
Yeah, I can't. Oh
Because,
God, wait.
yeah, you have.
Yeah, I don't want to like go. I have to think about it. How to restore this stuff because
You need to do some counting.
the plan was to that I pull out this term and then U reconstitute itself, and then I have this term, right? And U will just I can submultiplicativity, pull out U. And I have my error here.
But can't we, because we have u, and can't we just subtract u, h, the full u minus the k, sum up to k to get the remainder? That's what we wanted. Or we start from there.
I mean, I'm thinking about a little bit more complicated calculation where this works.
Did you write it in the code paper like this?
Yeah. I don't want to complicate it right now to look for the error.
You said k prime in the, not k.
No, this doesn't
Maybe
save
K
us.
prime
No,
starts from-
it doesn't save us. How can I? So am I? Oh God, is this like?
I think you.
So one question is whether you intended to pull out that factorial also, or you just wanted to pull out n plus 1. Because then you can still have the factorial there.
I think I want to pull out factorial. I messed up some stuff here.
Maybe we need a break.
I messed up something here.
I think you can do this kind of bounding for those terms, and then you will just bound your remainder from the top. And this would be sufficient. Because probably you couldn't calculate.
There is a more elegant way to do it, I'm sure. But that's probably what has to happen here. That's probably what has
Is the
to
result
happen.
correct, or like the last result?
Look, if n is a positive number, like Hubert wrote, right? So it's this is correct. This is correct, right?
Yes.
This is correct. So if I got rid of n here, this fixed n, right? I would restore my, right? And but what this n does, it makes the denominator smaller, right? So if I just throw away n, I get something that bounces from above. Okay?
Yes.
And then I get my, so I would have to write here this. And this would be correct. Although I think there's I'm bothered by this, that it didn't come out. Because I got here from, okay, I don't want to go into details how I got here, but there is a,
I think it will be too good if you can calculate the remainder explicitly as a
actually,
finite, because then you have a remainder as not as a series, but as a finite sum. And this is weird.
no, it's not,
Yeah,
it's not, I mean, you have u is infinite sum.
Yeah, but those u's will cancel out, like, yeah?
Yeah, because
You have
I'm,
evolution operator.
but they cancel when I do another bounding, because I have to submultiplicativity, use submultiplicativity.
Okay.
It's not so free. Okay?
Yeah, right.
It's not so free. Okay, we can fix it. We can fix it by doing this. So we are here. So we are here. Okay, we can now from above. We pull out this guy and the factorial 1 plus. So we basically drop n's from. Okay, we drop n's. This raises, decreases denominator, therefore raises each term, increases each term. And we will get 1ITH.
So there you're actually writing the bounding function there. You may not have actually taken the factor out. Then you skip the step where you were assuming that that's the bounding one. Oh, no.
What?
And that step where we had the confusion, where was that the actual bounding function, bounding series? Because the previous step, you might have put the common correctly, and then you use this as the bounding series.
I'm too confused.
Okay,
Sorry.
it's fine, yeah.
Okay, so we can fix it. Okay, we can fix it by doing shenanigans with the denominator. We can restore the form of the.
Restore the balance.
We can restore the balance. Okay, so we are here again. So you know. Okay, no. Thanks for catching this. Thanks for catching this. That's good. Okay. Good to know right now, because I have to check some stuff now. So when I go in June on the conference, I don't make complete fool out of myself. Okay.
Just a partial.
Yeah, just a partial fool. Okay, so we have the denominator,
Fullness of completeness of fullness.
submultiplicativity, so we can factor out the u, and we get our the remainder here, minus I t
H.
h n plus 1 and the factorial. And this will cancel nicely, and we get our remainder. So our remainder is th power n plus 1 divided by n plus 1 factorial. So this is bound for error. Okay, we cured by doing the approximation. And as you can see, what is going on here, I mean, okay, if we just pull out some numbers here, so th to power n plus 1, okay, so this is our dimensionless parameter, the norm of t times h. So it scales with time. Okay, longer time, the bigger this guy is, and to the power n plus 1. So this is a pretty steep increase, right? However, it is battling for dominance with a factorial. And factorial always wins.
I'm reading like epic book. They are battling this denominator over
Factorial
dominance of.
I think factorial would be a boss. It's really
It's more stronger.
So if you want to
nobody can hold.
imagine how this thing looks, right? I mean, there is a, if I drew some kind of like a, n, and here would be the magnitude, the remainder. So this would go like there will be some maximal value at for some n critical, I don't know how to call it, and then it will just get violently suppressed by the factorial, right? But there is this moment where the factorial is not winning yet. Okay, and where is this moment? It depends on the value of th, right?
So we have to destroy.
If th is small, this bump might not even happen. If this th is big, it will be moved towards larger and larger then. So there is there's a maximum of pain of inaccuracy you will get.
So again, these bounds also depend on the time. So that's
Yes.
Because now
I mean, he's spoiling everything.
Because when you look at papers, whenever they apply these approximations, they never bother about time. They just tell up to the kind of you.
But it's a function of time, so it
that's
depends
what.
on time.
The point is that actually matters.
No, that's why he's red flags, his alarm bells are ringing because it's like, is it a perturbation theory? If the strength of the perturbation depends on time.
It's not perturbation. He's right. It's just
He is right, but let me get to the point where I say this, okay? Because I prepared a story here, There was a story.
Yes, violently suppressed.
Violent, but epic.
Yeah, I mean, there is a battle here in the heavens, We had drama. We had a drama, That said, the heroes were laid low by difficulties, by the evil miscalculation. But we managed to.
Suspension of story. We can give it to ChatGPT to visualize it.
Yeah, but we can visualize it ourselves. But we managed to find to defeat we rallied our strength. We find the solution, and now we are going for victory. It's like a hero's journey. Everything is good in this world. Okay, so this is the estimate of the error. When you take n terms, this is the estimate of the error. You see that it's sometimes there is a maximum value somewhere, so it's probably taking more is better. More terms probably. I mean, you already knew that more terms will give you better results, but you know there is some optimal n, okay, or unoptimal n, let's say, for given time, which is of course kind of problematic if you think of it as a perturbation theory. But so the other to flip this on the head a little bit, you know, so the error, like, it changes with n for given time. So now so this is how much payoff we get for a given amount of work. But now let's add a different question, given some accuracy, how much work we have to put in. So what is the n? If I say I want to be 10% accurate, I want this error to be 0.1, what is the value of n for given t and h I need to take to achieve this accuracy? So the optimal the optimal answer would be that this n is the threshold value from our definitions of convergence. Okay, but this is like a theoretical, mathematical thing. It exists, but where is it? We don't know. Okay, the best we can do, we try to estimate it somehow, find it more or less where it is. Okay, so let's try to do that then. So what n for given error epsilon, which is epsilon, which let's, you know, it's greater than 0, but small. Let's not, you know, 300% error. That would be silly. So let's think we want to be accurate. Okay. So we can estimate. So we can estimate a little bit better. Okay. Right. So here are some things I managed to cook up. Okay. Because it was like it's not like I didn't see it in some textbooks or stuff like that. So as you know, I just played with some things I knew. So I want to share. So epsilon is supposed to be, it will be small, so we expect n to be, okay, first comment. If time is short, if if this is small, okay, that's why it's nice to use t time h, because we don't have to how many milliseconds or whatever. So this is the parameter, okay? If this is small, achieving any accuracy goal is very simple, okay? So if t is much smaller than 1, then already n equals 2 gives you error of order of 10%, I believe, 10%. So it's like, because you have 6 factorial in the denominator and you have something very small to power 3, it's kind of around 10%. You get something like this.
Yeah, but that also depends on the norm of h, right?
Yeah, the norm is suspect.
Directly say that it's going to suppress by due to the factorial nature.
No, t times h is smaller than 1. This is a number, dimensionless number.
Yeah, but then, so my point is, you cannot just simply say time. It also depends on the norm of h. How much is what you like.
But then this number is small. Whichever norm you pick, whatever. It's small. It's connected to the spectrum anyway, right? But this is like you just take a couple of n's to get however low you want to go. 3 n equals 3, 2, 4. It's fine. Things change when you are in the opposite regime, when this is actually like bigger than 1. Because now the powers of the numerator starts growing instead of getting smaller, right? So now this is where regime where you fight factorial fights with the the denominator fights with the numerator for dominance. Okay, factorial wins, always wins in the end, but there is a point, there is an inflection point somewhere, right? Because this can get bigger, 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 but its rate of growth is just cannot match factorial. So let's say that this is, we have this, error is small, so we expect n to be quite big. So let's say that n is large, n large. At least n is bigger than th, okay? I want big N so that I can approximate factorial with how the guy is called Stirling's approximation. Very famous Stirling approximation.
It isn't very famous. I didn't know about it until I read the plans.
Really? I don't
It
know.
wasn't that famous. I didn't know the Stirling engine before.
Stirling engine.
Stirling approx.
Because I heard like whenever you learn statistics, this is the
Yeah,
first thing.
even in thermodynamics.
Yeah, the log. Yeah.
Yeah, exactly. So it's like
Log Stirling.
it was always there in the background, approximating factorial with something
The number of microstates.
with something weird. So if we do Stirling approximation to the factorial in the denominator, you get 1 over 2 pi n plus 1 square root to u1 factor, and this is super weird. You get e, but the Euler number, e to power 1, 2.73, blah, blah, blah. It's just e.
Pi is also weird.
Pi is also weird, but I mean, something, you integrate something, some Gaussian, blah, 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 2 pi is expected. It's only expected. By e, it's kind of weird.
Yeah.
You have to admit, e is weird. Divided by n plus 1 to power n plus 1. So this is hellish, okay? If you want to now say that this is smaller than epsilon, and what is n? So that this inequality, it's kind of hellish. So let's simplify it a bit, because n is big, so n plus 1 is almost n. This factor here, 2 pi square root, it's order of 1. Let's just drop it. Let's say that this is more or less e th divided by n to power n. This is the order of magnitude that's kind of agreed. The real deal, the real difficulty here is the scaling with n, you know, and we preserve all the scalings with n here. So now we want to say that this thing, what is n? N such that this thing here, n is smaller than given epsilon, which is a small number. This is, of course, difficult to solve, or I would dare say that it is impossible to solve exactly, but we can guesstimate it a bit. You know, do some guesstimation. So for one, we know for sure, you know, if this has to be small, so n at least should be greater than e times th, right? So that this is less than 1. So that the powers are getting smaller, and we can have a chance to reach some small number, be smaller than some small number on the right-hand side. But what would you say if I said, what if we tried an epsilon that I will set, so it should be bigger than th, okay, this is like a necessity here, but how much bigger? Let me say here natural logarithm of 1 over epsilon. Just a wild guess.
That's right.
Okay? Why this particular number? Because then you can do the following calculation. Let's take logarithm of 1 over logarithm of 1 over epsilon. Okay, this is basically the denominator here, to the power e times th times logarithm of 1 over epsilon. I'm doing some calculations, okay? It will make sense. So this thing equals, unless you find another mistake, minus e th, okay? Because I'm using logarithm to get the power from here to in front. Logarithm 1 over epsilon. And logarithm of logarithm 1 over epsilon. A lot of stuff. No, this one is unnecessary. So this is a negative number, okay? Negative number. Epsilon is small, so those logarithms are big. I mean big-ish, because logarithms grow very slowly. So these are big-ish. And this guy is more big than this guy, okay? But what big logarithm means that we are more negative. So to increase this number, I can write that this is smaller than minus e th times logarithm of 1 over epsilon, right? I just got rid of this guy, which was a big number, so it made this more negative. So when I just throw away this guy, I get less negative number. So the inequality goes in this way. Okay, mind bending, maybe. So I can go even more. This is the thing I'm doing. So let me just get rid of this as well. And then I get logarithm 1 over epsilon, okay, equal to logarithm of epsilon, okay. Now what this means, it means that if I set n greater than this n epsilon equal to e times th logarithm 1 over epsilon, then because of this, I can write with some confidence that th to power n plus 1 divided by n plus 1 factorial, which is approximately e to power t times, what I'm writing, to power n will be smaller than epsilon. Okay? Because what I wrote here is a logarithm of this guy when I substitute for n this guesstimation. Okay? And smaller than logarithm, so I just exponent both sides, and here I arrived. So this is of course, so this is how much work we have to do to achieve accuracy of epsilon, okay? And this is not an optimal solution. We guesstimated, so this is probably too much work. You can do less to get to this epsilon that someone gave us, but it already tells us some things about what is going on. So I have some estimations here. So for one thing, we see that the longer the time, you have linear scaling with time. The longer the time, the more terms you have to calculate to achieve the given accuracy. So, for example,
you have the lower bound here. It means you cannot achieve better accuracy by this n.
I see it's not lower bound. Okay. If I take this n, I get smaller than epsilon, but I could get smaller n This is overestimation of n, okay? The optimal would be smaller, even smaller, right? The real one would be smaller.
Yeah, but if you know the optimum and then we can use it actually. Problem is we don't know the optimum and right?
Yeah, we
That's
don't
why
know.
We are guessing it.
We're guessing because we cannot calculate. Optimal would be smaller,
Yeah.
right? But for example, if you want accuracy of 1%, okay, for time h of order 2, okay, so bigger than 1, I estimate that you would have to calculate around 25 terms. It's kind of bad. And if you want to go to t of order 4, so twice the time, that would mean you would the same accuracy, but time twice as long. That would mean you have to go to n, 50 terms. Super inefficient. I mean, it's like so much calculation.
But at least linear with time.
Linear with time. And the coefficient, the scaling with accuracy is also like slowly growing. So if I want to, scaling with time is very expensive, but scaling with accuracy is less expensive because it's this logarithm of 1 over epsilon. So if I want to go...
In reality, you will achieve 1% of accuracy, less than 50. On your calculation.
I mean, yeah. Probably yes.
How much?
So maybe 47 would give you maybe, or maybe.
No, maybe because the distance between every term of the sequence will close enough to each other. Maybe at 28.
I don't know, maybe.
Yeah.
Who knows? We don't. With our estimation.
27 or 28.
Because any two becoming close, that's Cauchy sequence. Right?
Yeah.
So we have Cauchy.
Yeah, we have.
I mean, we have the error is this. This is all the information.
I know it's factorial.
Yeah. So it's like maybe this is a gross overestimation, perhaps. But the scaling with time, linear scaling at least, that's probably unavoidable.
Okay.
But with accuracy, it's better because if you want to go from here to, let's say, accuracy 0.5%, right? So we want time, let's say 2, but accuracy twice as accurate. That would require only plus 4 terms, because this guy here is very slowly increasing. So 29 terms to have 0.5%. But nevertheless, it's not good. It's not good. I mean, there is a lot of terms has to be calculated. This is not an efficient thing to do. So you know what? I thought I will finish this today, although we started a little bit later, so we can
just continue until
We can have a coffee.
Coffee?
It's to that.
Coffee.
So the issue evidently is the time. The longer the time, okay. So let's make a coffee break. I actually will. Yeah, but let's continue on with this whole shebang. So here the issue is with time, long time, a lot of times it's like ugh. But what if we could somehow circumvent this issue? And actually Hubert already, he was asking me about some stuff that he was like coming up with some ideas, and that's basically, he converged to the same idea. Because the evolution operators, they have the feature of composition rule, right? So if time is long, but we can, cut up our evolution operator into segments. We can cut up them into segments that are short intervals of time. So, in other words,
The method of trotterization.
That's a.
Don't spoil.
Oh no, it's not.
Trotterization is actually when you have like two parts of the Hamiltonian that don't commute,
Oh, yeah.
and you want to like calculate them independently, and to avoid commutators, you short times. Unfortunately,
Assume that
because I'm very slow.
showed that the commutator doesn't matter. Yeah?
Yeah, because it's higher order correction. Because I am very slow, this will be next semester, okay? Because it's related to Magnus expansion. Yeah, because I'm very slow. The plan was to talk about it
You are just
today.
dividing into very short times.
Yeah, I'm doing the opposite. I'm dividing into very long times, going around.
That's why it's not converging.
Yeah. Yeah, exactly. Composition rule. So composition rule means that, we have a th, and t is long, big. However, this equals th, t over 2, th, t over 2. Oh, this is shorter. And you can do it however many times you want. So you can get something like this. t over n to the power n. Okay? So the idea is this, that perhaps, if you make these intervals short, that means that you have to add a small number of terms. Okay? The price you pay for this, that maybe you are adding smaller number of terms, but then you have to multiply n such sums. But maybe there is some sweet spot where the multiplication is less expensive than adding up terms, calculating new terms and adding them up. Okay, so maybe there is a balancing act there, where you can, the sequence, the partial sum is this and this size, and then multiplying a couple of them is actually less expensive than, adding 7 times more terms. Going from 25 to 50, kind of expensive, but maybe multiplying 25 by 25 is less expensive, or maybe even like multiplying 4 times, you add 5 terms and multiply them 4 times. Maybe this is even less expensive. Or maybe not, maybe it's actually more expensive. That depends, of course, on the details, how big matrices you are using, how many terms there are, the shape of the Hamiltonian and stuff like that. But this is this is like a way to maybe circumvent long evolution times. So I made here some kind of calculation. I try to estimate the error. Now I'm very shy of showing the calculation because maybe we'll find another mistake. So I'll just flash. So my estimation was, and besides we are way over time, and this is not very important, I think. And in the notes you can check my calculation and point out all the mistakes I made. So the estimation I did. So again, you estimate the error as usual. This kind of formula, and according to my calculations, this actually scales like 1 over n to power smaller. Wait, sorry. N. Okay, so you slice it up, and each slice you approximate with partial sum of n terms, okay? And then you multiply. So that's the approximation. Because if there was just h here, that would be 0. Because it would be exact result. So capital N to power small n, th n plus 1, n plus 1 factorial plus something of order n minus n let's call this error of just one. So this is the magnitude. Okay, so this thing here, this epsilon here, is a is this error we estimated previously. Okay. So basically, this is error of one of the slices. Okay, this is the scaling factor with number of slices and square it. Where is it? Okay. So this is the first order of error. This is higher order correction. So the point was to show that there is a benefit, for dividing into smaller chunks. You can make the error smaller. Okay, even with this n is not very big, so you sum up not many terms. But you will have this amplification factor, or well, the opposite, attenuation factor of, how many slices you're making. The question is how expensive it is to actually execute the calculations, right? This is just estimation of errors. However, I mean, you see this amplification and it makes you. Let's just push it to the limit. Just go as large n as possible. Clearly, this is very, this is a way to drop the error however we wish, right? Mm-hmm. So we slice it so much that let's say we just need to add one term in your series, in each slice. Okay, so you are getting, so in other words, you are getting something like this. 1 minus ith divided by n, because times, the short times, n. And, limit n to infinity. Okay? That would be the logical extreme of this approach. You slice it into so many terms that it's enough to just take the first term of your series. It's a very small term, and just power n. But if you are doing this, you start to getting into a realm of just numerical integration, basically. Okay. So this is instead of doing calculations, perturbation theory, you're just doing numerical calculation, because this limit is actually exists, and this is just e to it h. This is just evolution operator. We just
surprise.
Right. If you could.
Isn't it actually how the e is defined?
This is another definition of exponent, right?
I think the one that you are given in high school at first is pretty cool.
Right. So this actually brings us to this what you spoiled. That what we are doing here.
If you want to minimize the error, you get the exact.
Yeah, I mean, if this is the approach, which is the basic perturbation theory, just summing up your series. So you're fulfilling the contract of convergence, basically. Well, it's not really a perturbation theory. What we are doing, we are just doing numerical
just truncating
calculations.
Truncating the series. They're just finding smart ways to truncate the series.
Yeah, or even not smart. We are just the most basic way of just numerically calculating stuff. There is nothing smart about it. So this is I called it perturbation theory 2.5 perturbative interpretation. Interpretation of evolution. So what I propose to you is barely deserved the name of perturbation theory, because right, especially this example, this is just a numerical calculation, okay? Basically, we just defined a procedure which you follow to minimize error, right? Something, the procedure that could be just put and given to unthinking machine to just execute it. And actually doing it by hand would be super stupid. You know, adding 50 terms and then 50 more to get longer times this is just something for machines. This is numerical method, not really perturbation theory. Because the real perturbation theory would be something of this sort that for one, as the name suggests, there should be some perturbation somewhere. Okay, and the perturbation is typically perturbation. What we mean by perturbation is that you go from your Hamiltonian, unperturbed Hamiltonian, and there you add some additional term. And like this term, you think of it as small. Small perturbation. Yeah, usually you somehow compare to what's going on without it, right? And then the real perturbation theory would try to not give you like a prescription for numerical calculation of something like u h plus lambda v of t, not numerics for that, but rather to represent the effects of this adding this perturbation onto the dynamics of the unperturbed system in a way that's understandable for humans. So that you can look at what's going on and, maybe explain something or maybe generalize something, not for unthinking machines, but rather to represent effects of this in a way that we can look and understand. And ideally, maybe calculate like 1 or 2 orders or something like that, not 25. So if we wanted to like put the basic perturbation theory from before, to translate it into this framework, then there are a couple of unfortunate things we would have to do. First of all, we'd have to admit that basically the Hamiltonian is the perturbation. The Hamiltonian itself is the perturbation because we just had our Hamiltonian. So the thing we did above, it translated into this would be like the base Hamiltonian would be just zero operator and the perturbation would be Hamiltonian itself. So this is already very stupid, right? This is not fitting this mold. The other thing that's problematic is that the magnitude of this artificial perturbation scales with time. The longer the time, the stronger the perturbation. That's also completely orthogonal to the usual way you want to think about perturbation theories. Okay, so basically, it's what you already noticed, that what we discussed above is not really a proper perturbation, not really a scenario for proper perturbation theory. But nevertheless, we can still, like, if time is short, this perturbation or the evolution is small. So in this context, it's kind of possible to, still think of it as some kind of perturbation theory. Then you just, you don't have to add too many terms. You kind of see what's going on there. So it's like we can use it as a test bed, maybe of like getting a feel of how would this thing could be translated into something that's understandable for humans rather than just a prescription for numerical integration of stuff, right? So what I'm trying to say here is basically that can we do the exercise when we take this our partial sums and somehow translate them into some pictures? Because what I'm talking about is some diagrammatology, okay? Because the understandable for human representation, what I'm basically saying that you have you're constructing your perturbation theory, you want to quantify effects it has on the dynamics of unperturbed system. You have some idea for constructing the series, which you then want to sum up. And maybe you can, the series you are constructing, this procedure gives you some terms that have certain pattern, which maybe you can represent in the form of diagrams, so that the human can look at it and get some feel for what's going on. And this is like very often what is executed. You look for diagrammatic rules. And then instead of like doing calculations, you draw some diagrams, and from this you try to like estimate errors, magnitudes, and ultimately translate them back into some mathematical expressions that can be calculated in the end and give you some values. But thinking to be done on the level of pictograms, essentially. Okay? And this, even though this is not really, our case is not really a proper perturbation theory, you can still try to have some fun and draw some diagrams if we can. And I have this, I cooked up a little bit of like this kind of representation for us to have some little fun. So if you permit me,
Yes.
5 more minutes, let's say. We started 20 past, or even 30 past, if I remember. So it's like
Due to the apocalypse.
due to the apocalypse, yeah. So let us nevertheless treat our. We don't have perturbation. We don't have this. So this guy, our evolution operator. Let's say time is short. So we imagine that this n is rather small. It's like, let's say 2 or 3.
Just a clarification regarding the notation. So now this h, is it including the v or?
This is UH.
No, the h that you're writing here, is it h plus lambda v or?
No.
Without perturbation?
H is H. If there's perturbation, there will be explicitly plus lambda.
Yeah, the full Hamiltonian.
I don't feel the need to have a special letter for Hamiltonian with perturbation, at least for now. So there is no perturbation right now. I mean, the Hamiltonian itself is the perturbation. So we will have, we have our, zero order term, which is just identity. We have first order term, which is minus ITH, second order term, minus t squared divided by 2h squared. And let's not go further, okay? So these are mathematical expressions. You can sum them up to get our result with some accuracy. If t is small, that would be even good accuracy. But the idea is to like interpret them somehow, maybe translate them into some diagrams. So the zero order is very easy to interpret. Okay, this is the part that does nothing. So this is as if there was no dynamics, if there was no everything is static. Okay, so the zero order represents of when nothing happens. Okay, let's put that into. Let's remember that. The first order guy, there is a way to like reinterpret it in the fun way. So we have this guy, it's ITH, but this thing, I can convert t into an integral. IH. What letter S? Okay, this is true. Constant thing integrated. It's just t, right? But then I can do even more with this. Integral is a Riemann sum, right? So I can like n to infinity the Riemann partitions sum k from 1 to n, such that I have identity n minus k t over n h 1 k minus 1. Okay, Riemann integral tells me I can write it as a sum of n I minus h t over delta t over n, right? So that the small the increment of time, and I can like sandwich it with identities. So if I write it like this, then the interpretation is as follows. I mean, I can imagine it like this. So I take my interval of time t and partition it into n small subintervals. So I have, you know, kt over n to k plus 1 t over n. I have a large number of this kind of intervals, right?
So the endpoint is excluded.
Endpoint is what?
The endpoint is excluded.
Yeah, I mean, this is how, you know, Riemann integrals work, right? Then I can imagine. This term is an accumulation, the sum over k, of effects where there is like nothing happens for most of the time, right? Because of one identities, except for the one moment in time at kt over n, when this impulse, infinitesimal impulse perturbation kicks in, and then we will go back to nothing happens until the time ends. So we have like the impulse happens at the first step, the impulse at the second, third, and so on. And you sum up all those things. Okay? There's, you know, it's kind of artificial here, but you know, bear with me. You see it? Kinda.
So this moment when it kicks, is just one moment per, let's say, per expansion simply. So when, in the sense like this term u1t, yeah, it has only one kick, yes?
Yeah, one kick, but in it's a sum of kicks, small kicks at all the, you know, the first moment in time, the second. I mean, the first and nothing.
In one moment, the kick will happen. All others are empty.
Yeah.
No kicking always, and only one kick at a specific time, and this specific time is actually.
So if we do some diagrammatology, let's say nothing happens, let's draw it with just a dash. You know, nothing happens, a dash. The infinitesimal, the kick, h, let's assign it x. Okay? All right? Pictures. Yeah. So we'd have zero order. So we could start writing our t approximately. Zero order would be like one identity. So we would have like dash, some number of times, you know, n times. Okay, let's fix some n. Don't have to go to infinity. It's just nothing happens. Then first order would be you would have kick, dash, for example, plus dash kick, dash, plus dash, impulse, dash, plus dash,
was a lie.
dash, kick, dash, plus.
Oh yeah, we got it.
You got it? I don't know, maybe you're slow, you know. Can you
with the last term, you haven't wrote the last term.
Yeah.
without
you were just missing one, just write the last one. Oh, now it's clear.
Now I get it.
So now what is the second order? How second order would look like without calculating?
Perhaps two kicks.
But different
And
combinations,
dash,
different
dash,
possibilities, permutations.
Dash.
Exactly.
Dash.
So kick, dash, dash.
Dash,
Plus.
kick.
It's a kick, dash, kick,
Yeah.
All combinations.
Dash.
and so on,
Again, it's
right?
No, that's right.
I don't get it.
Yeah, but here, like the kicks are like it's combination, not permutation.
Yeah, and
Right?
exactly. With like if exchanging kicks gives you a double contribution or not.
No, shoot.
Yeah, this is a question. This is a very important question actually. When I want
I
to.
guess that's what taken care of by the factorial.
If you exchange, I mean, you know, those correspond to some.
I mean, Hubert, we are working BEC, we are indistinguishable particles, so we don't.
You know, this corresponds to this kind of. Here are the terms. So I just put in the thing here, and this is my expression. So exchanging x's.
Doesn't matter.
Doesn't matter.
It's a combination.
Okay.
Okay, you can figure this out. So the point of this is exactly why you use diagrammatic methods. Okay, I can calculate you and show that this kind of decomposition for the second order. I can do it. Look. So it squared. This is the second order, right? But the second order, I can just write it as, you know, 1/2 t d s1 dt s2 minus ih. The same trick, right? But then, if you know something about time ordering and integrals of time, you should know, you see such a thing here, this is something that does not depend on time actually. You can order this integral. T ds2 s2 ds1. Okay, you absorb the factor here, right? Sh. And then you do the Riemann bullshit, and goes to infinity, and you convert it into two sums.
Yeah.
K2, K1, and you have 1, and that's so on, and you will have one kick here, and the one kick, it's some ones here, and kick, and so on and so forth, and you get here. So the point, I think the point is made, kinda. The fact you have your diagrams, you see the pattern. To get higher order, you didn't have to do the calculation. We knew what would have to put there, right? Because there we have diagrammatic rules. We know how the diagrams are constructed. I mean, we'll feel it intuitively. Or would someone would have to tell us, you know, if the Feynman rules, you would call them. So you could construct all the diagrams of arbitrary order according to those rules. Then you can translate them back into mathematics to actually do the calculations. But even sometimes you don't have to calculate to prove something. You know, is the exchanging means something, or we didn't have to actually go through all this to immediately understand that, no, it doesn't matter. This is the same diagram, and so on and so forth. So this is the point of diagrammatic method. This is what the point of perturbation theory is. You want to have your thing translated, represented in this kind of, some kind of diagrammatic stuff, so that you can look at it, imagine what it does, and the calculations are done at the very end, you know. You just want some quantitative results, so you just have to calculate something. But what's going on, it should be clear on the level of pictures, okay? When you have this, you have good perturbation theory. And the perturbation theory is also good when, you know, you don't have to go to 17th order. Yeah. Second, third maybe is good. So when your perturbation theory is constructed out of, you know, where time comes in explicitly, that's probably bad. Okay, because you want to, let's say you want to describe evolution over some time, but now the longer you wait, then, you know, your perturbation theory changes, your perturbation getting stronger, that's bad. You probably want to have something that's independent of time, which is what you pointed out. That And this is, you can do stuff like that typically because this is the perturbation in reality. It's not the whole Hamiltonian, that's just nonsense. And then you can let's say you can solve the unperturbed stuff explicitly, and then you can add on top of that the perturbation. The perturbation you can represent as diagrams, and it's like for each time, for all times, it's always good to, let's say, add a couple of diagrams, and that's all you need to do. That's the ideology, and that is also a practice of doing perturbation theories. And this is only an illustration, okay, of a bad, and we are trying to do perturbation theory on bad example, essentially, of numerical integration.
So just a question. So this is the essence of Feynman diagrams, if I'm right, or is it completely off?
Feynman diagrams, you have a Dyson series type of perturbation theory in field theories, and the Feynman diagrams are exactly
these kicks and
this is the you try to express the terms in your series through pictures, and the structure is not this simple. Okay, there's something. The terms are constructed in, there's some procedure for constructing those terms, and they can be broken down into a certain way. There are patterns forming that can be translated into pictures, not one-dimensional pictures, okay? This is this is very simplistic. That's why there's no structure, there's just Hamiltonian, arbitrary operator. We don't know what it has no moving parts, so the structure can only be like one-dimensional, pictures stringed together in a chain. But if there is something going on, it starts to, explode into some more complicated kind of some tree or some other thing. Okay, but this is the Feynman diagrams is basically human readable representation of Dyson series terms. Sure.
That's why it's very wrong if people connect the Feynman diagrams to physical processes, I believe.
This is actually, I agree.
I just mean there is this common problem that people draw a diagram showing, for example, electron coming, proton coming, and annihilation. They say, oh, this is what happened there. Yeah, they just met and they annihilated. But no, it's just a term from the perturbation or expansion of the physical situation that is going on here, which is, by the way, maybe dominant, but it's not something that is physically happening there. Yeah, so.
Yeah, this is a trap to think that your pictures represent something more.
Because they are so appealing, you like to think, oh, this is what's physically going on.
Yeah, I never thought about it like that.
The particle flies in.
Now you already know the particle trajectory at what time the position is and so on.
Yeah,
in the meantime they create a pair, this pair and then go away.
So then people are aware that this is kind of shaky. Interpreting this in this way is of course shaky. So there are no real particles. These are just virtual particles. So we can do some, but this is just
Trying to give meaning to things.
Exactly. Not all pieces of. You can have some formula that, in its entirety, has interpretation. Does not mean that pieces of this formula also have to have interpretations. This is the lesson from the first part of this whole course, and this is doubly true for diagrams in your expansions.
But on the other hand, I sometimes wonder, because if I could be able to kind of a measurement device and measure in the middle, for example, of these two particles interacting, whatever, and maybe I will see these virtual particles there. Maybe it is just that they are there, but we couldn't measure them. I think there was some momentum conservation problem.
No, if they were there, they would become virtual.
Look,
sorry?
If they were there, they wouldn't become virtual. It's
But
just
how do you know that they are virtual? They could be there for the moment. You do not investigate the collision.
No, it's just effective way of seeing this. This is not the entire physics. Like,
Well, why
No,
not?
guys,
Maybe it is.
let me answer this, because you are trying to construct a counterfactual. What happened if I did something else? The answer is, if you wanted to describe a situation when you were actually doing measurement at this point, you would have to change what you know.
Yeah, okay.
Modeling.
It wouldn't be this perturbation theory is with those kind of diagrams. This is, let's say, evolution operator.
Okay,
This would change. The diagrams would change.
Something else, that maybe the quantum state is evolving via.
There is no quantum state.
Maybe. Whatever. But I know, but it means that there is a physical situation. The physical situation, call it, what I mean by a quantum state. The physical situation is evolving via such, where in between there is a probability of, let's say, those virtual particles being there physically, simply. So this is what I meant by, if I came with a measurement device and I make a very magical measurement in the middle of this process, I may encounter this situation.
To make this into more.
So just a suspect. I could suspect maybe it's physical.
So I believe if you want to make it more sensible, you would say the following. So here I have something, and this thing is described by this perturbation theory. There are diagrams. There are a couple of diagrams. I'm interested in interpreting. So now, if there is a situation when I'm doing some measurements. Okay, now we switch context. Now some experiment, there is some measurement, and so on and so forth. And now I do calculate the Born rule, probability, whatever. And let's say the whole calculation can be broken down, that this probability equals maybe some modulus square of particular diagram. The same kind of diagram as before. If this happens, if this is like the accidentally, or maybe not accidentally, this is actually what happens, then you may start to, okay, wait. So maybe if this diagram describes this situation with measurement, so maybe I can make some connection now with this more full perturbation theory of some different context. Maybe, but this is probably more coincidence than actual explanations. Okay.
Because maybe as a contra example, not a contra but a stronger example, is what I am doing when I'm telling stories that there is the process of atom being excited for a moment to that excited state and then quickly coming back to a ground state. Yeah, and this, at least as we believe, is physical. We indeed have those processes of atom going via excited state and in my framework. So I just thought now, like, okay, so maybe those Feynman diagrams, which is apparently the same, the same but the corresponding concept.
I would say that you have no reason to say that it's happening. You could have a process where it goes up and goes down.
Something different. If there is no excited state, this process couldn't happen. So on the other hand, if there is no photon field in the electrodynamic, you do not have annihilation or interaction via annihilation, creation of a pair of proton and positron electron. Yeah, positron electron. So perhaps.
But when
and saying that this is just existence, not a physicalness. It's just the existence of the excited state. It's the fact that it is utilized at some point.
This kind of touches, hopefully, although I'm starting to be more and more doubtful, we get to Schrieffer-Wolff, which would be next lecture. This is kind of connected to effective theories. You use this effective term in Hamiltonian, it looks like the matrix elements, blah, 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 that you would expect in the also description of this kind of excitation. Is it, what it means, can you draw parallels? Can you say that this is the same thing?
Yeah.
This is kind of difficult, and I would be very, very skeptical of drawing such parallels.
But the name even here, it's an effective theory. So it's telling you that what is going on physically is actually those excitations.
This is you have no reason to say this.
Well, I do have, because I have a full Hamiltonian, which I know that is true. I don't know if my effective Hamiltonian will be true. It will be true in some context.
No. You over interpreting things.
Maybe, but on the other hand,
there is no.
On the other hand, I would claim that I have strong reasons to phrase it like this. Especially that it's not only if existence of those excited states
I would say
affects the system, like the existence of electric field, electromagnetic field affects that processes. It means that it is involved. It's not so that it's just existing and it's magically blessing the system that, oh, I'm here so you can have this.
I mean, there is a sure, but it's not like the thing I would caution against is to like really, because you can imagine, okay, those two low-lying states are coupled in this and that way because it's like there is a high energy shell there where there are like virtual excitations can happen and so on and so forth because there are perturbations there, matrix elements that are active and so on. This is you. When you say this, you are describing what you are seeing in your Schrieffer-Wolff transformation, basically. But and this is fine as long as you don't try to. If you want to conclude from this that there is like a resolution of time when you will probing your system in such a way that you can actually catch this process happening and you want to conclude something from this, or maybe I can transfer some information thanks to that and blah blah blah. This I wouldn't claim that it's indeed happening like excitation, but I would claim that indeed a small fraction of this excited state, like 0.01%, for example, is being occupied. So the true state of the system is not the ground, but the ground plus a very, very little admixture of this excited, because otherwise it all depends what you want to do with this claim. If you want to, build upon it some theory, or is just using it to this is key here, because you can go too far. This is the thing comes to mind. The error where you make like this is you have your collapse rule.
Yeah, the very celebrated
one. The celebrated, infamous collapse rule, which is like a formal device you do when you do some calculations of Born rule for sequential measurements and stuff like that. And now, when you start saying, okay, but this is a process that happens because this is the wave function is collapsing, blah blah blah, and you start treating it seriously, you can now construct scenarios based on that this is a real process that happens in some space-time point. And, you construct paradoxes if you want, and you basically poison the well for the foundations of quantum mechanics for whole eternity. This is the issue with extrapolating too much from some rule of thumb explanation of some formal manipulations happening inside some other formula that has interpretation.
Yeah, I agree. That's why I raised it in the beginning that Feynman diagrams are not physical processes. But I just insist that they could be, that they are physical scenarios in which exactly such a process can happen.
Well, this is...
of course, you will agree that I can excite this atom to excited state and then de-excited, and it would be a physical process, physical scheme. I will just shine one laser, shine the other laser.
They might happen in some scale that needs another effective theory to explain. It doesn't not that the picture you have, the full picture, getting everything. There is another scale of energy that the physics you are describing happening, and there is an effective quantum theory that explains it.
with its own set of diagrams.
Yeah, exactly.
Effective
That could
here,
be like
the word
that.
effective refers to the fact that something effectively happens as the second order process.
If some physical phenomena happens
Look.
that is not catched by your effective theory, but you think it exists and can be described in another theory, that theory might exist, yes, of course. But it needs another effective theory to like model it.
Yeah, but this is not what I'm talking about actually.
But also look,
Okay.
ultimately you probably want to say that I have my diagrams and I want to imagine the balls, ball particles moving like that and bouncing off each other. That's probably what ultimately this is what you want to say.
Physics, they are pretty good locales, so you know.
No, and this is because you have this picture. It suggests that there are balls, classical balls moving around. So the rule of thumb is okay. If you want to imagine quantum processes in terms of classical balls, you can't. And every attempt to doing that is inherently flawed.
That's a wave. Yeah, it doesn't matter if it's a cloud coming or a ball coming.
It's not that even. Okay, if you keep it contained, you don't extrapolate too much from this. You don't treat it as a basis for jump off point to create your own sub theory of quantum theory, like bomb pilot wave stuff and things like that. Then it's fine. But when you are doing stuff like this, you want to extrapolate too much, you are just asking for trouble. Okay, so you have to be very careful about that. It might be possible, but you have to be extremely careful. You have to know on the philosophical level what you are doing. But the rule that don't put too much like interpretation into diagrams is a good rule of thumb. Okay, don't you can try to explain to layman some processes using diagrams.
Yeah, this is what I do usually.
But this is only for people.
Atom being excited, although I know that it's not so exactly.
Yeah, but this is like if your listener will forget it in 2 days, that's fine. But if you want to educate students like that, that's bad because they start building up. Also, I can actually think of my quantum processes as balls bouncing off each other. It's just they just insist to doing some weird stuff with it, but it's just balls bouncing off each other. That's harmful. Okay. It's better to rip the band-aid off and say, you cannot. Just don't even try. It's just, there's some limits when they go into balls. This is a classical limit, that's different beast. Here is a quantum processes. It's just, pictures is the best you can do right now. But don't assign too much meaning to them.
It's 1 p.m.
It's 1 p.m. Nice. Only 1 hour overtime.
No, it's not 1 p.m. It's 3 minutes.
Your diagrams are
Stuff is not converging. Okay, guys. Thank you for your patience.